The Constitution of India. Preamble. We, the people of India, having solemnly resolved to constitute India into a sovereign, socialist, secular, democratic republic and to secure to all its citizens justice, social, economic and political, liberty of thought, expression, belief, faith and worship, equality of status and of opportunity, and to promote among them all fraternity, assuring the dignity of the individual and the unity and integrity of the nation. In our Constituent Assembly, this 26th day of November 1949, do hereby adopt, enact and give to ourselves this Constitution.
Happy morning, students. So, I think you all had your Navratri celebration, 9 days of Navratri plus Vijayadashmi. Yesterday we had a Google Meet with all the teachers, Principal Sir, Dr. Balambika Ma'am. We had a session just to recall our Winners Day celebration, how we used to do for the Kalolsavam call, the cup for our school, and definitely we were missing you children. And I know that is the most important day for us because that marks the day of positive vibes in us. We used to exchange our positive energy among ourselves. But definitely children, this cause will have a solution and we are looking forward for it. And be happy always, think positive, visualize your presence in school. Very soon that is going to happen. That is what I believe. My children in front of me, very soon that is going to happen. Right? So today's class will be starting with 16th group elements. And last class we were seeing phosphorus, its preparation, allotropes and also about oxides of phosphorus. In 16th group elements we know we have oxygen, sulfur, tellurium, but main thing we are going to focus only on oxygen and sulfur for this year. If you talk about the atomic radii or ionic radii, we know that is the distance between the nucleus and the electron present in the last shell. So as the number of shells increases down the group, definitely the atomic radii will also increase down the group. So what will happen to ionization energy? As the number of shells increases, you need very less energy to remove the electron from the outermost shell. So ionization energy will decrease. So Miduna, what will happen to electronegativity? Yes, we know oxygen should be having a high electronegativity, but little less as compared to that of fluorine, which is the highest electronegative element in the periodic table. But this electronegativity will also decrease when you go down the group. And what will happen to electron gain enthalpy, Ardra? Yes, these elements will definitely have a tendency to accept electrons. So, the negative electron gain enthalpy will be there, but that also will decrease when we go down the group. And if you come to the physical properties, not all are metals and non-metals. We have metals, non-metals, metalloids, and also we have solid, liquids and gaseous states which are present in the 16th group element. Oxidation state, if you see in common, they exhibit -2 oxidation state, but they can also exhibit positive oxidation state, which we have already studied in +1 class. If you see the positive oxidation state especially given by oxygen, it is just because of the anomalous behavior. That is due to two simple reasons, small energy and high electronegativity. Why this happens? It is just because of hydrogen and oxygen forming an intramolecular hydrogen bonding, which cannot be possible in H2S. So because of these simple reasons of its small size and difference in the electronegativity, oxygen exhibits a different exceptional character as compared to other elements in that same group. If you see the reactivity with hydrogen, oxygen and halogens, with hydrogen they form hydrides. Not all the hydrides have the reducing property, have got the oxidizing property. That is, except water, all the hydrides have reducing property. And they have an acidic character because their bond enthalpy is very low, means the energy required to break the bond or make the bond is very, very less. So when it goes down the group, it decreases. So their thermal stability decreases and their reducing property increases. which thereby increases the acidic character of the hydrides. If you see oxides, they form two type of oxides, EO2 and EO3, out of which ozone and sulfur dioxide are gases. We have selenium dioxide being a solid, in which their reducing property decreases when you go down the group, and to make sure that all the oxides are definitely acidic in character. What about halogens? They can form three type of halides, dihalides, tetrahalides and hexahalides, out of which only hexafluorides are very stable, rest of the hexahalides are unstable, and most of the hexafluorides are gaseous in nature. We know hexafluoride means definitely they form an octahedral structure. And when you come to tetrahalides, they have a trigonal bipyramidal structure with a lone pair of electrons, and dihalides, in that dichlorides and dibromides are formed with an sp3 hybridization being tetrahedral in nature. So these are the basic things that we should be knowing about 16th group elements. To be more precise, we will be learning about oxygen, ozone, sulfur and about its sulfur allotropic forms. So these are the things which we will be learning now. To know more about it, definitely you should be having your textbook, children, because this lesson, that is especially P block elements, when it starts and the next forthcoming chapters have got lot of reactions. So when I say reactions, don't get panic, don't get afraid. How you used to learn your multiplication tables, the same way we will be learning. What you should do, when I am taking ozone, you start writing the reactions along with me, learn the reactions by heart, because the preparations are the preparations which will not change. You cannot change the preparation. So that is always there, already prepared. So you should be learning it by heart so that you will remember. So when you write manually with your hand, instead of just mere reading from textbook, start writing in your notebook to learn more and more. You can also have a separate notebook for writing reactions and practicing it. So children, now we will get into ozone preparation. We will learn about oxygen. We also call it as dioxygen because two oxygen atoms are present in an oxygen molecule. Now how it can be prepared? We have three laboratory preparation, or you can say basic preparation of oxygen, where by heating the chlorates, nitrates and permanganates. So either you can heat the chlorates, nitrates or permanganate. When it is heated in presence of manganese dioxide, you get dioxygen. Potassium chloride, in presence of manganese dioxide, when it is heated, you get potassium chloride and dioxygen. The next one is a thermal decomposition of metal oxides. That is an electrochemical series. We have low metal oxides and high metal oxides. So when they undergo thermal decomposition, you get your dioxygen. It can be lead oxide, it can be silver oxide, it can be mercuric oxide. So mercuric oxide, when it is heated, when it undergoes thermal decomposition, that is by heating, it decomposes to form mercury and also releases dioxygen gas. And the next one is with hydrogen peroxide, again undergoes decomposition to give water and dioxygen. You can also prepare dioxygen with electrolysis of water, where again hydrogen and oxygen gas are being liberated at different electrodes. So these are the basic preparations that you should be knowing with dioxygen. Now when you come to properties, definitely we know it is a colorless, odorless gas. It supports lot of marine life, that is dissolved oxygen. Aquatic life is sustained just because of the presence of dioxygen in water. It has three stable isotopes also, because we know what are isotopes, having same atomic number but different mass number. You can see oxygen 16, 17 and 18, which is given in your textbook. When I write these hints, please underline the same in your textbook, children. We know oxygen, when we were drawing this molecular orbital theory, you remember children in +1 MOT, we know in spite of having an even number of electrons, oxygen shows paramagnetic character. Antibonding, bonding minus antibonding by 2. Remember children? So that is just because of the unpaired electrons. Though it has even number of electrons, it has unpaired electrons, and because of that it has paramagnetic character. This oxygen has got a variety of reactions where it can react with metals, it can react with non-metals, and also it can be catalytically oxidized one compound to another compound. If you see with metals, it reacts with calcium to form calcium oxide. Even it reacts with non-metals like carbon to form carbon dioxide. It catalytically, that is in presence of a catalyst like vanadium pentoxide, it reacts with sulfur dioxide to get itself oxidized to sulfur trioxide. In your textbook, you have some reactions with aluminium, phosphorus, zinc and methane. These 5 reactions are very important, children. You should be knowing at least to write basically 1 or 2 reactions with metals, non-metals and compounds. So this will be helping you to write the property of oxygen. Uses, variety of uses of oxygen. If you see for respiration, breathing, and also for plants, it gives out oxygen. And also if you see in oxygen cylinders used in hospitals, so many applications, it supports combustion. So different applications are there with dioxygen. Now we will learn about simple oxides of oxygen and then we'll get back into ozone.
Dioxygen. Which gas present in the air supports all life forms? If you thought oxygen, you are right. But did you know that the chemical name of atmospheric oxygen is actually dioxygen? So what's the difference between oxygen and dioxygen? Technically, oxygen refers to the element oxygen represented by the symbol O in the periodic table, while dioxygen refers to the molecular form of oxygen represented by the symbol O2. Although dioxygen is found abundantly in the atmosphere, it can also be prepared in the laboratory. So how is dioxygen prepared? What are the chemical equations involved? Let's find out. Dioxygen can be prepared in the laboratory by 3 methods: decomposition of oxygen-containing salts, thermal decomposition of metal oxides, and decomposition of hydrogen peroxide. Click each image to learn more. In the first method, dioxygen is prepared from an oxygen-containing salt, such as mercuric oxide. Mercuric oxide in powdered form is taken in a test tube and heated over a Bunsen burner. Mercuric oxide burns in air to decompose into mercury and dioxygen. Mercury gets collected in the test tube as a molten mass. Dioxygen is released as a gas. The presence of oxygen can be confirmed by holding a glowing matchstick at the mouth of the test tube. The matchstick begins to burn brighter. In the second method, dioxygen is prepared by thermal decomposition of a metal oxide, such as potassium chlorate. 4 parts of potassium chlorate are mixed with 1 part of manganese dioxide, and the powdered mixture is put in a test tube. The mouth of the tube is closed with a cork. The cork has an inlet through which a delivery tube is passed. The test tube is then fitted to a stand in a slanting position. The other end of the delivery tube is immersed in water in a trough and covered with a beehive shelf. An inverted jar, half filled with water, is placed on top of the beehive shelf. Next, The mixture in the test tube is heated for a few minutes over a Bunsen burner. Heating potassium chlorate releases a gas, which travels through the delivery tube and collects in the inverted jar. The presence of gas is indicated by bubbles coming out of the delivery tube. The gas obtained is dioxygen. In this reaction, potassium chlorate burns in air to decompose into potassium chloride, along with the release of dioxygen. Manganese dioxide acts as a catalyst. In the third method, dioxygen is prepared by decomposition of hydrogen peroxide. Powdered manganese dioxide is taken in a flat-bottomed flask. The mouth of the flask is closed with a stopper with two inlets. Through one inlet, a dropping funnel is introduced, and through the other inlet, a delivery tube is passed. The other end of the delivery tube is immersed in water in a trough. The end of the delivery tube in the trough is covered with a beehive shelf. An inverted jar, half filled with water, is placed on top of the beehive shelf. To start the process, hydrogen peroxide is put in the bulb of the dropping funnel. Then the stopcock of the funnel is opened slightly so that the hydrogen peroxide falls drop by drop onto the manganese dioxide. Hydrogen peroxide reacts with manganese dioxide, releasing a gas, which travels through the delivery tube and collects in the inverted jar. The presence of gas is indicated by bubbles coming out of the delivery tube. The gas produced is oxygen. In this reaction, hydrogen peroxide decomposes into oxygen to form water and dioxygen. Manganese dioxide acts as a catalyst.
Now we will see about simple oxides. Now what are oxides? A binary compound of oxygen, when it combines with an element, you call it as an oxide. Like calcium with oxygen, it forms calcium oxide. So any compound of oxygen, when it combines with an element, you call it as an oxide. Now this oxides, it can be simple and it can be mixed. Simple oxides, like example magnesium oxide and aluminium trioxide. Mixed you have lead oxide and iron oxide. This is magnetite, an ore of iron. Now simple oxides, it can be acidic, basic, and also it can be amphoteric. When an oxide combines with water, when it combines with water, if it gives an acid, you call that as acidic in nature. Example like sulfur dioxide, when it combines with water, it forms H2SO3. So this is an acid, so this oxide will be acidic in nature. Examples like non-metal oxides are acidic in nature. Metal oxides with higher oxidation state can be acidic. The same oxide, when it combines with water, if it gives a base, then you call it as a basic oxide. Any oxide, when it combines with a water, when it gives a base, it has a basic property. Example like calcium oxide, when it combines with water, you get calcium hydroxide. We know calcium hydroxide is a base, it is alkaline in nature. So calcium oxide is basic. All the metal oxides will be basic in character. Now these metal oxides, there are some metal oxides which shows both acidic and basic property, that is dual nature. Such oxides we call it as amphoteric oxide. What are amphoteric oxides? Amphoteric oxides are those which has both acidic and basic character. So these are called as amphoteric oxide. Example, you can take it Al2O3. Apart from acidic oxide, basic oxide, amphoteric oxide, you have something which is called as neutral oxides. When I say neutral, It does not show any acidic character, does not show any basic character. So, it is neither acidic nor basic. Such oxides we call it as neutral oxides. Example, carbon monoxide, nitric oxide, CONO are examples of neutral oxides. So, these are very important, children. You may be asked to write in 2 marks the simple oxides of oxygen, that is with oxygen. So, you can write any examples of acidic, basic, amphoteric and neutral. Now, we will learn about ozone.
Ozone layer. Earth's atmosphere is divided into 4 layers: the troposphere, the stratosphere, the mesosphere, and the exosphere. The stratosphere contains the ozone layer. The ozone layer consists of relatively large amounts of ozone molecules. This layer protects the Earth from harmful ultraviolet radiation emitted by the sun. Ozone is made up of 3 oxygen atoms, O3, in contrast to the ordinary oxygen molecules, which consist of 2 oxygen atoms, O2. Ozone molecules form when energy from ultraviolet radiation separates the 2 atoms in an oxygen molecule. The separate oxygen atoms then recombine with oxygen molecules to form ozone. The formation and destruction of ozone happens continuously at the same rate. As a result of this equilibrium, the amount of ozone in the atmosphere remains essentially the same. Although ozone molecules are only a tiny fraction of the molecules in the atmosphere, ozone plays a vital role in shielding life from harmful effects of ultraviolet radiation from the sun. Humans release into the atmosphere many chemicals, such as chlorofluorocarbons, CFCs, that damage the ozone layer. As a result, more ultraviolet radiation reaches the Earth's surface. This happens when chlorofluorocarbons absorb UV radiation and decompose, releasing a reactive chlorine-free radical. The liberated chlorine-free radical reacts with an ozone molecule to form an oxygen molecule and a chlorine monoxide radical. The chlorine monoxide then reacts with an oxygen atom, producing chlorine radical and an oxygen molecule. The new chlorine-free radical is then able to consume another ozone molecule. The resulting chain reaction depletes the ozone layer, thereby exposing the planet to the UV radiation. Exposure to UV radiation causes sunburn, infection, premature aging of skin, and other harmful diseases such as skin cancer. Since the depletion of ozone layer is a serious issue, countries all over the world have agreed to a treaty called the Montreal Protocol banning use of chlorofluorocarbons. This treaty will reduce the production and use of ozone-destroying chemicals. Summary: ozone is a triatomic molecule consisting of 3 oxygen atoms. The ozone layer prevents harmful UV radiation from reaching the Earth's surface.
We'll get into ozone. Ozone. It has got 3 oxygen atoms. Now, how it is prepared? That is by heating this dioxygen in a silent electric discharge. When you do it in silent electric discharge, the purpose is it gives ozone, and the process is endothermic, means lot of heat is being absorbed. So, to prevent the decomposition of that, to prevent the decomposition of ozone, it should always be taken in the silent electric discharge tube. Now, if you see the properties, it has a gaseous state, it exists in liquid and also in solid. That is pale blue gas, deep blue liquid, dark blue liquid, and a violet black solid. And it has, of course, a small smell odor is there present for ozone, and when it is present in small concentrations, it is harmless, does not cause any harm to the atmosphere or also the people. But when the concentration becomes more, when it increases, it slightly start causing headache and also nausea. Nausea means a tendency to vomit. And it is thermodynamically unstable. It is not that stable when you compare to oxygen, and when it is in high concentration, it becomes highly explosive. It can even burst out. And this ozone can immediately decompose to form dioxygen, and it liberates nascent oxygen, means oxygen with a single atom is called as a nascent oxygen. So it acts as a powerful oxidizing agent. So it can oxidize any compound like lead sulfide. When it combines with ozone, it gives lead sulfate. So it oxidizes lead sulfide to lead sulfate here. The next one is a very important reaction to estimate the presence of ozone gas. That is, ozone, when it is treated with excess of potassium iodide, that is, which is being buffered. We know what is a buffered solution, where the acidic and the basic character coincides together. So those buffered solution, it liberates iodine, and this iodine, when it is titrated with sodium thiosulfate, you can estimate the amount of oxygen gas that is liberated. And the next one is these nitric oxide, which has been coming out with the exhaust of the jet aeroplanes. They tend to combine with the ozone and it gives out oxygen gas. And also, you know, this freons which are used in refrigerators, right, refrigerants, those are also may cause depleting in the ozone layer, which is really dangerous for us in the future. And so we have to be very careful with the use of all those. And next one, if you see the structure of ozone, this we have studied in the last year, children. Lewis dot structure also we studied. It has got a resonance hybrid. What do you mean by resonance? That is, there are 2-3 structures which are hypothetical, means confusing. You cannot confirm that this is the structure of that particular compound. Such a structure we call it as a resonance or hypothetical structures. So here if you see, the dots represents the electrons that are present around the atom. So if you see, the double bond gets shifted here and there, and you use this double headed arrow to show that these are resonance in nature. So these are the 2 resonance structures of ozone. And uses, if you see, it is used as germicide, it is used as disinfectant, and it acts as an oxidizing agent also. So now we will learn about sulfur, it forms, and about sulfur dioxide and sulfuric acid.
Properties of ozone. High above the Earth, in the stratosphere, is a layer of an extraordinary gas. This gas is called ozone. Ozone plays a major role in preventing the harmful ultraviolet or UV rays of the sun from penetrating the Earth's surface. Let's learn about the properties of ozone. First, let's look at the physical properties of ozone. Click each tab to know more. Ozone occurs naturally in the stratosphere, where it is formed from atmospheric oxygen in the presence of sunlight. Pure ozone is a pale blue-colored gas. In liquid form, it is dark blue in color, and in solid form, it is violet black. Ozone has a pungent, bleach-like odor. When inhaled, it can cause nausea.
and headache. Ozone is slightly soluble in water. It is most soluble in inert, non-polar solvents such as carbon tetrachloride and fluorocarbons, with which it forms a blue solution. Under standard atmospheric temperature and pressure, ozone is an unstable gas that decomposes readily into molecular oxygen. Now, let's look at the chemical properties of ozone. Click each tab to know more. Ozone acts as a powerful oxidizing agent. It is unstable and, on warming, it decomposes into oxygen. Ozone oxidizes nitric oxide to nitrogen dioxide. Ozone oxidizes sulfides to sulfates. For example, lead sulfide to lead sulfate. Ozone oxidizes potassium iodide to iodine. This reaction is often used as a test for ozone.
We will learn about sulfur. Sulfur, if you see, it has allotropes, yellow rhombic sulfur and monoclinic sulfur, which is basically called as alpha sulfur and beta sulfur. Alpha sulfur is more stable as compared to that of beta sulfur, which is above heated with 369 Kelvin, it becomes a beta, that is monoclinic sulfur. Now, how to prepare alpha sulfur? That is roll sulfur, an ordinary sulfur, when it is a solution in CS2, when that is evaporated, you get your yellow sulfur, that is rhombic sulfur. It is insoluble in water, but it is soluble in benzene, alcohol and ether. When you come to beta sulfur, it is soluble in carbon disulfide, and there is a temperature which we call it as a transition temperature, where 369 Kelvin, below which alpha sulfur is more stable, above which beta sulfur is more stable. That is, above 369 Kelvin, beta sulfur exists, and below 369 Kelvin, alpha sulfur exists. So, such a temperature we call it as a transition temperature. And how to prepare this beta sulfur? We know alpha sulfur, when it is heated or melted above 369 Kelvin, it is in the form of a crust, and when holes are made in the crust and when you pour out the liquid, you will get needles shaped molecules which are called as beta sulfur, or we also call it as monoclinic sulfur. There are two forms which is given in your textbook, both are important. One is S8 and other one is S6. S8, you can see 1, 2, 3, 4, 5, 6, 7, 8. 8 sulfur atoms forming a puckered or crown shaped structure, and you have S6 which is forming a chair structure, and the dimensions are also given in the textbook to you. They may just ask you to draw the two forms of allotropes of sulfur to you, so you may just learn the two forms by heart. Now we will learn about sulfur dioxide.
Allotropes of sulfur. Some elements like carbon, phosphorus and sulfur exist in two or more distinct forms. This property of an element to exist in two or more distinct forms is called allotropy. Let's learn about the allotropes of sulfur in detail. Sulfur exists in different allotropic forms in nature. The three different allotropes of sulfur are rhombic sulfur, monoclinic sulfur, plastic sulfur. Click each tab to learn more. Rhombic sulfur, also called alpha sulfur, is the most stable form of sulfur. It exists as S8 molecules. 8 sulfur atoms are linked to form a puckered ring structure. Rhombic sulfur is prepared from rolled sulfur. A solution of rolled sulfur and carbon disulfide is prepared. The solution is filtered through a filter paper. The filtrate obtained is then evaporated. On cooling, the remnants, pale yellow transparent octahedral crystals of rhombic sulfur are obtained. Rhombic sulfur is bright yellow with a melting point of 385.8 Kelvin. It is insoluble in water, sparingly soluble in organic solvents like benzene, alcohol and ether, but readily soluble in carbon disulfide. Monoclinic sulfur is also called beta sulfur. In monoclinic sulfur too, the sulfur atoms are linked to form a puckered ring structure. Monoclinic sulfur can be prepared from rhombic sulfur. Rhombic sulfur is melted. The molten rhombic sulfur is allowed to cool till a part of the liquid gets solidified and forms a crust. The remaining liquid is poured out by making holes in the crust. The needle-shaped pale yellow transparent crystals formed are called monoclinic sulfur. This sulfur is a dull yellow with a melting point of 393 Kelvin. Monoclinic sulfur dissolves in carbon disulfide.
Now we will learn about sulfur dioxide. SO2 is its chemical formula. Sulfur, when it is just burnt in oxygen, you get sulfur dioxide, which is a simple yeast preparation of sulfur dioxide. In laboratory, when sulfite is being treated with dilute sulfuric acid, you get water with the liberation of sulfur dioxide. And industrial preparation, any sulfide ore, when it is burnt in oxygen or when it is oxidized, you get sulfur dioxide gas again liberated. So these are the basic preparation of sulfur dioxide. If you see the properties, it's a colorless gas with a pungent smell. It has a pungent odor and it is soluble in water just because of the reason when it is dissolved in water, it forms an acid. Remember children, we were studying this in oxides. That is, sulfur dioxide, when treated with water, it forms sulfuric acid. So this is a acidic oxide, and it also reacts with base to form sodium sulfite. Sodium hydroxide, when it is treated with sulfur dioxide, you get sodium sulfite and water. Now this sodium sulfite, which again when hydrolyzed in water and treated with sulfur dioxide, you get sodium hydrogen sulfite. So for the preparation of sodium hydrogen sulfite, you can react sodium hydroxide with sulfur dioxide. The next one is a very important preparation of thionyl chloride, also called as sulfuryl chloride. SO2, when it is treated with halogen, that is chlorine, you get SO2Cl2. And the next one, which we have already learned, catalytic oxidation. SO2 undergoes oxidation in presence of a catalyst like vanadium pentoxide to give sulfur trioxide. Next one is a use of sulfur dioxide as a reducing agent, where you can see Fe3 plus get reduced to Fe2 plus. So here it acts as a reducing agent by reacting with a ferric ion and then giving ferrous ion. Coming to the structure of sulfur dioxide, just like ozone, it has an angular structure with lone pair of electrons above sulfur, and it has a resonance structure where these two structures are hypothetical, means you cannot confirm the real structure of sulfur dioxide. So, these form an angular structure of resonance hybrid. And uses, if you see, it is used in refining petroleum. Liquid sulfur dioxide is used as a solvent, and you have so many uses where it is used as a disinfectant also. So, now we will just see about oxoacids of sulfur, children. I will just try to put a video where you have 4 different oxoacids of sulfur, which you should be knowing the structure that is just given in your textbook, 4 basic structures of oxoacids. Now, we will learn about sulfuric acid. With that, we can wind up the class for today.
Chemical properties of sulfur dioxide. Sulfur dioxide is a dense, colorless gas that is soluble in water and occurs naturally during volcanic activity. Not only is it highly toxic, but its odor is suffocating and unpleasant, with the smell of burnt matches. It is a major component of acid rain, as it mixes with water vapor in the atmosphere to produce sulfuric acid. Let's conduct a simple experiment that will allow us to see some chemical properties of sulfur dioxide. For the purpose of our experiment, we will use sodium sulfite and hydrochloric acid, because they are both common chemicals that would be encountered in an industrial setting. First, we will place a burning match near the mouth of a jar filled with sulfur dioxide gas. The matchstick will be extinguished quickly, showing us that sulfur dioxide is non-combustible. Now, we will place a burning magnesium strip near the mouth of the jar containing the gas. You will notice the metal will burn brightly with a blue flame. During this reaction, the high heat produced by the burning metal will dissociate sulfur dioxide into sulfur and oxygen. The released oxygen will aid in the combustion of magnesium, forming magnesium oxide. Let's check the pH of sulfur dioxide. Once again, using the jar filled with sulfur dioxide, we will insert a moist blue litmus paper. The gas will turn the blue litmus red. If we leave the paper in the jar for an extended period, the paper will turn white, with the gas having bleached the paper. This reaction shows that sulfur dioxide is acidic. Sulfur dioxide will react with alkalis to produce sulfite salts. If sulfur dioxide gas is passed into a calcium hydroxide solution, the bubbling sulfur dioxide will initially dissolve in water to form sulfurous acid. Sulfurous acid will then react with calcium hydroxide to form calcium sulfide. The equation will be sulfur dioxide plus calcium hydroxide yields calcium sulfide plus water. When sulfur dioxide is bubbled through the alkali, sodium hydroxide, the result will be the formation of sodium sulfite salt. When sulfur dioxide gas is bubbled through sodium carbonate in water, sodium bisulfite and carbon dioxide will be the product. Sodium bisulfite is used as a food additive. Summary: sulfur dioxide gas can be produced by heating a mixture of sodium sulfite and dilute hydrochloric acid. Sulfur dioxide gas is acidic. Sulfur dioxide will react with alkalis to produce sulfite salts.
We have come to the last part of today's class, which is sulfuric acid. This is a common acid term which we have learnt right from our 10th standard children, and you have learned something about sulfuric acid already in your 9th and 10th. The chemical formula is H2SO4. it is prepared in a 3-4 step process, which we call it as a contact process, where the first step is burning of sulfur or sulfide ores with oxygen to liberate sulfur dioxide. That is, you burn sulfur or sulfide ore in the presence of oxygen to form SO2. In the second step, SO2 is catalytically oxidized to SO3 using vanadium pentoxide as catalyst. In the third step, the SO3 thus formed in sulfuric acid will be absorbed to form oleum, which is H2S2O7, and the last step is diluting oleum with water to get the required concentration of sulfuric acid. So this process, if possible, I will be putting the video. You can refer the diagram that is given in the textbook. The 4 steps are important for you to understand the preparation of sulfuric acid. If you come to the properties, these are colorless, dense, oily liquid. It dissolves in water immediately with the evolution of large amount of heat, and it is low volatile in nature, that is not that easily escape into its vapor form. It has a strong acidic character, that is why it acts as a very good oxidizing agent. It has strong affinity towards water. That is a simple reason why when it dissolves in water, it forms hydronium ion and HSO4 ion, where again this HSO4 minus will dissolve in water to form H3O plus and SO4 2 minus. And because of this, in this reaction, the value of Ka being very high, that is the dissociation constant value is very high, so it can easily give its H plus ion. That shows it is a strongly acidic in nature. And if you see the uses, definitely it is used as an dehydrating agent. That is, when sugar in presence of mineral acid, you know what happens. It is given in your textbook. C12H22O11 giving charring taking place, 12 carbon plus water molecules. You remember we studied in 10th standard. Also with copper, sulfur and carbon, it reacts to form the required oxidizing forms of it. Right, it can react with both metals and non-metals, easily concentrated, but there are 2 forms of sulfuric acid, one being a dilute form, another being a concentrated form. There are some compounds or metals which can only react with concentrated sulfuric acid to get its product, which are necessary. And uses, if you see, sulfuric acid is a very important chemical, and it is used in detergent industry, in paints, in dye stuff, in metallurgical applications, storage of batteries. More applications are there. Even in our lab, we use this sulfuric acid for the qualitative analysis of salt. So this is being used widely even in volumetric preparation. So with this, sulfuric acid is over, children. The next class we will be learning about group 17 and 18 together. With that, this chapter will also get over. See, the notes for this chapter, as of the only preparation properties and uses are there. So you have to learn the preparations, and when you are learning property, definitely there are some reactions which are important as well. So learn the reactions by heart, learn the process that are involved, like contact process, Oswald process. Wherever the name of the process is there, you should be learning it by heart. Okay, if you have any doubt, please call me, children, and all the best for your preparation for your online exam. Don't get afraid, learn sincerely, give your 100%, definitely you will be getting good results. Okay, so wish you good luck, children, all the best. See you in the next class. Stay home, stay safe, take care, bye.
The contact process. Sulfuric acid is used in the making of fertilizers, car batteries, soaps and detergents. It is also used in the preparation of paints, inks, textiles and even medicines. Owing to its worldwide industrial application, sulfuric acid is called the king of chemicals. Sulfuric acid is commercially prepared using the contact process. This process involves 5 main steps: the production of sulfur dioxide, the purification of sulfur dioxide, the oxidation of sulfur dioxide to sulfur trioxide, the conversion of sulfur trioxide to oleum, and the dilution of oleum to sulfuric acid. Let's take a detailed look at the different steps involved in the contact process. The process starts in a tower called the Sulfur Burner. Sulfur powder or a sulfur ore, such as zinc sulfide or lead sulfide, is burnt in the air within this tower. Sulfur burns with a pale blue flame, producing a mixture of sulfur dioxide and oxygen. This mixture contains impurities such as dust particles and arsenious oxide, which need to be removed. These impurities are removed in the purification stage. In the purification stage, most of the dust particles are removed by passing the sulfur dioxide and oxygen through the dust precipitator. From the dust precipitator, it is sent into the washing and cooling tower, where the remaining dust particles are removed by spraying the rising gases with a jet of water. The gases that leave this tower are free of dust but are moist and still carry the impurities of arsenious oxide. The gases move into the drying tower, where they are sprayed with concentrated sulfuric acid. This process dries the moisture. The arsenious oxide is removed by passing the gases through an arsenic purifier containing gelatinous hydrated ferric oxide. The arsenious oxide gets absorbed into the purifier. Next, the sulfur dioxide and the oxygen are passed through a preheater to raise their temperature. The next step involves the catalytic oxidation of sulfur dioxide to sulfur trioxide. The oxidation of sulfur dioxide to form sulfur trioxide occurs in the catalytic converter in the presence of vanadium pentoxide, which acts as a catalyst. The reaction is exothermic and reversible. Contact process plants are generally operated at a pressure of 2 bar and a temperature of 720 Kelvin. The sulfur trioxide formed is converted to oleum in the next step. The sulfur trioxide from the catalytic converter is passed into the absorption tower, where it gets absorbed in a spray of concentrated sulfuric acid in the presence of a quartz catalyst to form oleum. The final step involves the conversion of oleum to sulfuric acid. The oleum is collected in a dilution tank containing water. The oleum is diluted with the required quantity of water to get sulfuric acid of the desired concentration. Sulfuric acid obtained by the contact process is 96 to 98% pure.